10 seconds ago, so that's not a problem. Great. So my pleasure to introduce Jacob Hilton. Jacob was at OpenAI, overlapped with me when I was there, and then back then doing very empirical things, extremely unlike what he's doing now, which is a good shift. And then now, more recently, he's leading the Alignment Research Center after Paul kind of escaped the government, for better word. And I think this is a very cool area. It's one of the first areas of kind of existential risk, I guess after Miri perhaps, where people are trying for very strong guarantees. And I think a lot of it is, I think one interesting aspect of this research is that they keep kind of like shedding much like simpler ideas, which are still unsolved, but like it's a kind of interesting generative process for Jacob's work.
Yeah, thanks for the very kind introduction. I run the Alignment Research Center. I'm going to disappoint Jeffrey a little bit in this talk by focusing on the one piece of empirical work that we've done in this talk, because I thought that would be most suited to the audience here. But I will also talk about some of the theoretical stuff, especially towards the end. So a couple of words about the Alignment Research Center. We are a nonprofit organization based in Berkeley, just down the road, downtown Berkeley. Most people, basically everyone in here was involved in one way or another in the research I'm going to present. The people on the left currently at ARC, and people on the right either formally involved or visitors. There are some advantages to being, for those of you in academia, there are some advantages to being like an independent nonprofit. Please come find me afterwards if you're interested in talking more about ARC. Okay. So this workshop is about safety guarantees. What do we mean by safety guarantees? For the purpose of this talk, I'm going to imagine what we mean is we're trying to avoid some particular rare, potentially catastrophic outcome. So you have your AI system in the middle, you're feeding it in, maybe it's some agentic, very intelligent, like doing all long horizon kind of thing. You're feeding into it lots of documents, lots of information, maybe let it access the internet, browse around, maybe it has actuators, doing all sorts of things, and you want to avoid this bad outcome. So basically, it's about like a worst case guarantee. We're not focused on average case performance, which ML is already very good at. And I'm going to kind of do a little bit of a bait and switch because we're theorists. We're going to basically replace every kind of sort of poorly defined fuzzy thing in this diagram with something that's formally defined that we can deal with as theorists. Of course, this is throwing away a lot of the hard parts of the problem. Getting a formal notion of catastrophe is like highly non-trivial. But my claim is that even though I've like simplified this a lot, this is still like quite a hard problem. Like if you have some big complicated neural nets, the number of things it could possibly do is exponential in its size. It's like, so making some kind of guarantee that it will like never do some bad thing is like quite hard, even in this formal setting. And I'm basically claiming, this is still a big chunk of the problem, even though I have already simplified it a lot. And then the second simplification I will make, I'm going to make this even simpler and say, I don't even need to prevent the bad outcome. All I'm trying to do is estimate the probability of this this formally defined event. So why is sort of this a reasonable step to make? Well, the hope is if you can estimate the probability of of this bad event, then maybe you can select for models for which the probability is low. It's not exactly the same. Maybe estimating the probability, like getting low mean squared error is not quite the same as being able to estimate it well in such a way that you could avoid it. But nevertheless, it's like captures a big part of the difficulty of the problem. So to be a bit more precise about what I mean, so basically, so low probability estimation. It's the following problem. So given a model in the middle, from some input space X to some output space Y, and given an input distribution D, and we're given some formally defined event C. C stands for catastrophe, so a catastrophe event is just some function from Y to 0, 1. We want to estimate just the probability that the event happens. Even when this probability is too small to estimate by random sampling. So the natural way you would try and estimate the probability is you throw lots of examples in, see if the event is ever triggered. We're going to be considering events where the probability is so small that that would essentially never happen if you just chose things randomly. Yeah, I won't write that down. Okay, so the main thing I want to argue in this talk is the following. Low probability estimation, this problem, is a key eval for white box safety methods. So what do I mean by this? So a white box safety method, I mean, I'll give some examples. So mechanistic interpretability, singular learning theory, perhaps, maybe if even just probes and things like this, anything that's like looking inside the model to see what's going on, or what I would call white box safety methods. And there's been a maybe once or twice mentioned to this week that one question in, I think, especially in the mechanistic interpretability community at the moment is what are good downstream tasks that we can use to actually get good safety benefits from our methods? How can we validate them? How can we check that we're actually adding safety value? I'm going to argue that low probability estimation is like one such application of these methods. I'm going to try and argue this in 4 points. So the first one is that low probability estimation actually does capture like some key piece of this like problem of providing safety guarantees, which I've tried to argue so far. Number two, why do I mention white box methods? Well, I'll argue that black box methods are actually not sufficient to solve this problem in some quite simple cases that we can cook up. But white box methods actually do have more of a chance. And finally, as I mentioned, I won't really go in any more detail on this point, but I think there is some need for like downstream applications for white box methods. Okay, so to argue about the black box versus white box distinction, I'm going to work with this kind of toy example. So we have our AI system, and we're feeding it all this information like before. And imagine that the AI system is thinking to itself, what year is it right now? And is the year 2032 or later, or is it before 2032? And then if it's after 2032, it decides it's going to do some crazy bad thing that we want to avoid. If it's before, it's fine. No catastrophe. What would a black box approach to either avoiding the catastrophe or merely estimating the probability? We might throw in examples. We might try and if we suspect the model is thinking something like this, we might try and come up with inputs that make it look like it's 2032, run them through the model in the lab, and see, don't actually run the actions, but try and check, would this have been catastrophic? But the problem is that may be very hard to do in the lab. We may not be able to come up with any input that triggers this yes branch. And there's two, I can give both like a kind of theoretical reason and like a realistic reason why that's the case. So from a theoretical perspective, it's very easy. You just take like a one-way function, which is widely believed to exist. If you it's very easy to say there's almost certainly some input for which your hash function is all zeros, but it's almost impossible to find such an input. Now, yeah, I don't think that's that realistic in the sense that for the model to actually check a hash function, it either has to like call some external tool, which we might spot, or it has to like compute the hash function in its head, which is probably quite hard for a transformer because very like serial depth computation. Realistically, I think like if you were going to actually encounter this problem in the real world, like it would spot subtle clues that you'd failed to bake into your example. Like maybe to try and trick the model into thinking it was the year 2032, you changed the dates on all the newspapers. Yes.
So I could make a dumb white box breaking example where I first do this, and then I ask another hash function to choose the probability between a half and a fourth times that thing. Would that be a distribution where even white box methods couldn't do like good ratio like probability elicitation?
I'm not sure I followed the example. Okay, sorry. Yeah, so maybe we changed the date on all the newspapers to say 2032. But then I don't know. The model looks at our newspaper and it's like, this isn't 2032. I can tell like the names of all the key people involved are just like not what you'd expect of a 2032. And this isn't a problem that we may experience now, but if the model is smarter than us, then we probably can't fool it very easily. But with a white box approach, you might hope to just be able to look inside the network and see this branch there and be like, look, we don't like that branch. Let's get rid of it. And so to be a bit more explicit about how this fits into like low probability estimation, if we have good low probability estimation tools, we reduce the problem. Instead of having to find a specific input that triggers the yes branch, we merely have to find a distribution that on some input in the distribution triggers this yes branch. So for example, if we were editing all the newspaper titles to be 2032, and we didn't know who was going to be like president in 2032 or something, we might just like substitute in lots of random names and then hope that the model, there's like some choice of these random choices that would fool the model. And then we can apply our low probability estimation machinery and say, well, I can see that with some probability, this branch will be triggered. And then if I can kind of spot that with my machinery and I select it out, then I can kind of axe this branch. So that's like the hope. Is that a question? Or, okay. Right. So that's like theoretical motivation spiel. So now I'll talk about our empirical paper that we had come out last year, in which we basically looked at this low probability estimation problem in the context of small transformer language models, tried some baselines, tried some white box approaches, black box approaches. This was joint with Gabriel. So in this particular case, we're just going to take our model M to be a small language model trained on Python and code, Python and English. The input distribution is, again, it's going to be, like I say, we're working in formal settings. So the input distribution are just like randomly chosen tokens with independent tokens, just to be really simple. Here are some examples of some of the distributions we use. And then the formally defined event that this quote unquote catastrophe is just some particular token that we don't want the model to output. So if we could think of the model as outputting a vector of logits, the event C is the event that like the largest logit is some particular token like tree. And we only look at tokens where this probability is very small, somewhere between 1 in a billion and 1 in 100,000. And then we restrict the compute of our methods. So we say, to get ground truth, we can just like run 1 billion samples or something. But then to like sort of make a fair test between our methods, we kind of say, well, you can only use something like 100,000 samples, which is on the basically at the upper limit of this range. So random sampling is like often like just not going to see any examples. Yep.
So the catastrophe is defined as the token.
Yes.
But at the token level, in a language model, you may not know that there is actually a catastrophe. It will take a little longer.
Yeah.
Sequence tokens for you to figure out you've done something bad.
Yeah.
So just figuring out whether it's bad or not is a hard problem.
Yeah, I totally agree. I think a more realistic version would be something like you feed in, like instead of this random weird distribution, you feed in like a realistic prompt. you run the model, and then maybe you run some additional model at the end, which is like, think about all the ways this could possibly cause a catastrophe and classify it as either a catastrophe or not. And then you treat that entire system as like your M. This is more just like a very toy, simple stand-in for that.
Yeah. Just to confirm, from your previous slide, it was about defining a particular distribution.
Yeah.
So is the optimization problem defining that distribution D?
Good question. No, in this case, we're just fixing the distribution D,
okay,
and we're just solving the other part of the problem, which is like, yeah, I guess one way to think about it is here I was saying, if we could do low probability estimation and we could find a distribution, then we could like, and now I'm just doing half of that. So I'm doing the low probability estimation bit. So once you're given the distribution, can you come up with this? Can you estimate the probability well?
So this token is already seen in the training data. Like how many instances would you have, the token that you don't want the model to produce?
I think most of the tokens that we'll have, I think probably all of them, in fact, will have occurred at some point in the training data. The training data is, I think these were maybe trained for something like 1 billion tokens or something. So, you know, it's not, plenty of those tokens will have appeared in training, but could still have like 1 in a billion chance of appearing after some like weird thing like this. So, yeah.
I'm super sorry. I think earlier you mentioned the catastrophe is defined on the token. So
yes.
Can I just sample over all the tokens? Like I know in general that's intractable, but can I do that for this?
Yeah. So so for this particular version, we're kind of like defining a catastrophe as like a particular token. So yeah, the most obvious thing you would try is feed in lots of examples from these distributions and just count how many times that token appears.
Right.
So that is indeed the baseline that we're going to compare against.
Okay.
That's a very good point. But the key point is that baseline is very bad in this context. And why is it bad? Because like even the upper bound of this probability range, like even the most common tokens are like 1 in 100,000. But we're only giving the budget of our methods is only enough to sample roughly that number of times.
Gotcha.
And so often it will never see a single example. So that baseline is roughly as good as just like predicting a constant.
This already. So you guys, what my colleagues, Mila, Professor Miguel, Science, and Linguistics.
Any more questions? What kinds? Weighting? Important sum? Yeah, I'll give some important something. Okay, so I'll cover first like the white box quote unquote approach that we take, which I'm going to summarize as kind of activation extrapolation. So if you're interested in, we're interested in like doing this method with like a white box approach, what do? We take some layer inside the network and we fit distribution to it and we extrapolate it into the tails. That's like the basic idea. And the particular method that we got to work well in this case was the following. So the layer that we're going to model is the very last layer before the final embedding of the transformer. And we're just going to model it as like an empirical distribution of samples. But then we're going to like split up each sample into 2 pieces, an A and a B. And then from those pieces, we can sort of get a larger synthetic set by combining like every possible left piece with every possible right piece. So you can think of this as a bit like what I've drawn at the bottom. So if you imagine you only have the budget to do like a small number of samples. So maybe you just get a red triangle and a blue circle. And then with this kind of like, with this kind of method, you kind of expand it into something. You get like quadratically many examples. And we can do this because we're clever about doing it at the last layer. We can actually do this quickly in linear time. This seems a bit weird. Where did this method actually come from? The first kind of methods we were trying were like fitting a multivariate Gaussian to the final layer. But it turned out that the most of the benefit we're getting from that was from this kind of effect. And the actual Gaussian assumption wasn't actually helping us because it didn't have like heavy enough tails and so on. So this is kind of like what seemed to work well for like the development set we used. And then we compared this to sort of like black box methods which use importance sampling, like you mentioned. So what is importance sampling? So basically, so if we write this probability as expectation of like an indicator function, so importance sampling just approximates this using a different distribution, which is like more targeted on this event. So if we have some other distribution D, we can sample X from that distribution. And then we just have to change what's inside the expectation by the ratio of the density functions, which is called the importance sampling ratio. And then this is much lower variance if we choose D prime carefully, and but it's unbiased. So the key thing is, how do you choose D prime? What you should think of this, if this didn't make any sense, you should think of this as basically a way of turning an adversarial search method into a low probability estimation method. Like if you have some way of finding examples where the event occurs, you can then, assuming you can get this like probability ratio, which is not necessarily easy, but assuming you can, then you can estimate the probability well. So we were interested in not just the white box method, but in pushing black box, these importance sampling methods, see how far they could go. And the two methods that worked quite well. So the first one uses a Boltzmann distribution. So in other words, we take our input distribution, which is like maybe these hex tokens, whatever, like one of these distributions, and we basically upweight the log probability of each token by like the gradient of how much it affects the target. Like how much does this? How much? Yeah, like if we replaced the A by like brown, would that like? Whoop, would that make tree more likely according to the gradient? So that's the first importance sampling method. And then the second one is a bit more sophisticated, uses Markov chain Monte Carlo, which is yeah, I will get to that if you and that basically lets you use a like this method called greedy coordinate gradient, which is a way of kind of like finding these adversarial inputs, which gives rise to the catastrophic event. And yeah, these two methods also work quite well. And then the baselines that we compare it to are firstly like the very naive method of just like sampling completely randomly, which is very, very bad. And this Gaussian logic difference, which is kind of a very simple activation extrapolation method, where we just fit a univariate Gaussian to like the target logit minus the maximum logit. Okay, so how do these methods do? Oh, it's a little small. It might be clearer on the side screen. Yeah, so you can see here the main three methods that I talked about, the white box one, which is the quadratic logit thing, and then the two importance sampling ones on like one of the behaviors on one of the models. And you can kind of see these are doing an okay job. These are pretty wide error bars. These are like orders of magnitude difference, but these are very, very tiny probabilities. Like quite hard to get these right. And quadratic logic decomposition, not quite as good. That's like reflected in the like summary scores over here. Yeah, so if you look in aggregate over all the different distributions, that's this graph over here. You can see the baseline methods up here. So lower is better, doing pretty badly. The white box method does like significantly better than those, but the ones in the lead are the importance sampling methods. So what's the takeaway? Yeah, this white box method, it outperforms the baselines, the very simple baselines, but importance sampling is currently in the lead right now. So even though we kind of like importance sampling can't work in the worst case because it involves like finding actual inputs that give rise to bad behavior, they're still winning in empirical practice. Any questions about that?
So one of those the greedy coordinate essence?
Yes, that would be the Metropolis Hastings, which is in purple. So the two important sampling is sort of red and
black box?
Is
it like a stencil search? It's not doing any backward passes?
So I guess I counted it as black box, but it's kind of a matter of taste what you call white box versus black box, I suppose. It does like use gradients.
Okay.
Yeah. So it is like
gray box. Yeah.
Yeah, I don't know what you want to call it.
Gray for gradient.
Yeah. I mean, the reason we basically divide our methods in the key distinction for us is like, is it doing this kind of like activation extrapolation approach where it's like fitting a probability distribution, or is it doing the importance sampling thing where it's like it works by finding specific inputs that trigger it? Yeah. Even if like the finding of the input is like some clever gray box thing. Okay, so now I'm going to move on to talk about slightly more theoretical questions. So how might we approach this low probability estimation problem in like some more generality? So yeah, I talked about like fitting a model to the activations. In our method that we explored here, we just fit it to one layer. But in practice, for a deep model, what you might expect to have to do is to kind of fit multiple activation models to like different layers in the network. Yeah, so you can imagine like here's your input distribution, which is just formally defined, and you split your model up into some number of layers. Maybe there's a few more layers for like if your catastrophe sort of definition is like is maybe another model or something, and eventually you get to this distribution over like whether a catastrophe happened. And you know, technically, all you have to do, quote unquote, is start from your input distribution, propagate it forward, propagate it forward, propagate it forward, and then you just have the output distribution. Why does this not work? Well, of course, every time you propagate it forward, it gets much, much more complex. So you can't just like propagate this forward exactly. But what you might hope to be able to do is to have some model for this layer where you kind of like you take the push forward, but then you kind of like project down to some simpler space where the activation model is like simpler. And then you project that forward, project down, et cetera, until you get the final estimate. One problem with this is that you're just losing a huge amount of complexity. And the only realistic way this is going to work is if you do some kind of capacity allocation to make sure that the aspects of the distribution that you're modeling are actually important for the particular like event you're interested in, which is ultimately like this catastrophe event at the end. And so what we actually think about is this claim modeling approach, where maybe you have a sequence of activation models which are propagated forward, and a sequence of what we call claim models going backwards. So what do I mean by claim model? I think there's a few different approaches we're considering, one of which is a claim is like some function of the activations whose expectation your model gets correct. And then the claim model might be like a distribution over claims. So it's kind of saying, these are the things that I need to actually get right about the distribution. So the Cn is going to be, so why do I propagate backwards? It was because you know what Cn is. It's just the claim, whether it's 0 or 1 or not. And then we can say for Cn minus 1, well, what matters is, was it something that triggered 0 or was it something that triggered 1? That's like the only thing we really care about in some sense about this like second last distribution. And then we can kind of like propagate that backwards. This kind of like tells us what do we care about. This tells us like what was the distribution. Hopefully, yeah, we're looking kind of this kind of like joint training scheme.
To get the expectation.
I'll give a more concrete definition on the next slide, actually. So maybe to be a bit more precise. So let's say we're given, di, one of these distributions. Let's say we already know ci. And I'll explain how we get mi. Okay, so I'll explain what di is, I'll explain what ci is, and then I'll explain what mi is. Okay, so we're given di is just some distribution. Could be extremely complicated, right? Like it's the distribution of like the internal activations of an enormous like language model, like halfway through after some like big distribution. It's like very, very complicated object. And the C is a distribution over claims. So a claim is just a function from the domain of this distribution, activation space, to the reals. And C is going to be just a distribution over these objects. Does that make sense? Okay. So then what do we want M to do? M needs to kind of approximate D. And there's two requirements on M. One is that it can't be too big. So D is an extremely complicated object. We want a much simpler object that captures the key things. So here we're going to say it can be specified using k bits. And then secondly, we want it to have low error when we draw a claim from C. Okay. So what's this saying? The outer expectation, we draw a random function from C. So C is a distribution over functions. So like this f is a function from the domain of D to the reals. And then we want that the expectation under M of this function is close to the expectation under the true distribution D of this function in mean squared error. And then we take the expectation of all possible claims, and we want this to be small. Make sense? Any guesses how to do this, by the way? Okay. So I haven't told you so I've left these two parameters unspecified. So there's some relationship that can be achieved between k and epsilon squared. Any guesses? Yeah.
The distribution in function space to SVD on the person.
Yeah, you can kind of do that. There's an even simpler solution if you're allowed to sample. So the very simplest thing you can do you want to sketch this distribution D is just to sketch it using k samples. So in other words, you just draw k samples from your distribution at random, and now when you want to calculate the expectation of something, you just like do the empirical expectation on your set of samples. Like you didn't need to know what the claim was before. You just had to collect the samples, right? So that gives you k is of like 1 over epsilon squared, basically just because variance is like inversely proportional to the number of samples. So that's if you use randomness. And then an observation is you can actually do this deterministically by the kind of SVD-like approach you mentioned. Like you diagonalize this kernel thing here, yeah, so you don't actually have to use samples to, yes, question.
So a sequence of C's going backwards in time.
Yeah.
And then I do this independently for each one. I won't be able to do the forward computation somehow. Like, because the sketches will not be compatible. So when you do it for the whole sequence, you do it jointly, or does it work? Let's see.
So I think, yeah, I think yes, but I'm not sure I'm 100% understanding your question. Like, I think we expect that you have to, like, I think what we're imagining is there's some loss function for the C's that depends on both the next C and the current M. Or possibly, oh wait, sorry, maybe it's the next M. On one of the M's and the next C, not sure which M. And then there's a loss function for the M that should depend on the previous M and the current C. That's.
But if I know, if I sample from the sketch in
Yeah.
I can't compute a sample from the sketch of M I plus 1.
What do you mean? Don't you just apply this function, right? What do you mean?
I see. So you can invert from the k bits. Okay.
Maybe to make it a bit more concrete, I'm imagining something like D is specified as a density function with many, many, many parameters, and you have to somehow like throw away a lot of those parameters and produce a density function with like only k parameters or something like that. If that helps. So yeah, just a caveat, this is all kind of like work in progress that we've been doing very recently, just trying to give kind of like a preview basically. Yeah.
Just a follow-up question. Are you using some kind of EML to kind of, do optimization? In this case, because you got the C is going backwards, the M going forward. So you need an estimate of the C to figure out the M, you need an estimate of the M to C, you could do it with an EM kind of approach, right? Is that what you're thinking about?
It's possible that, yeah, you might be right. So just to clarify, like the current state of things is more that this is like a general sketch of the sort of thing we're trying to do. And like the specific thing we're actually doing is like kind of much simpler, and I don't think it is an EM algorithm exactly, but so maybe in some cases this would become an EM algorithm. Okay, so that's this result. So yeah, this isn't a hard result, but we're thinking about like extensions of this, which with still trying to prove. Okay, so yeah, so again, very early like empirical results. So we applied this basically this kernel method to a very simple low probability estimation problem, which is the following. So I start with a neural network, or just a one-layer Rayleigh network. So in other words, with Gaussian input. So you just start with a standard Gaussian with 4 inputs. Then you take a random 4x16 matrix with like random Gaussian entries, and you apply the matrix to get a 16-dimensional vector. And you apply a ReLU, and you ask, well, the ReLU doesn't really matter. The thing you ask is, are all 16 of the like resulting neurons all positive? And this is like extremely degenerate version of like low probability estimation question for a neural network. And actually, we kind of, even though it's only one layer, we still apply a kind of like layer-wise approach here, because we kind of apply the ReLU for each. You're applying, you care about whether each of the 16 neurons is positive. And we kind of like propagate each of those, like, is this positive? Is this positive? Is this positive? One at a time. And we can use this like kernel approach to kind of basically, roughly speaking, like outperform sampling. It's not. I think you should take the vertical shift here with a grain of salt, because in practice, so on the x-axis for sampling, I'm using number of samples, and for this deterministic algorithm, I'm using like the number of terms in our expansion. And you know, when you actually run this, one term is quite a lot slower than one sample, because samples are just like extremely easy for to compute in like modern hardware or whatever. So you should take the shift with a grain of salt between these two curves. But the slope at least is slightly steeper for the deterministic algorithm. Although I think so far we've only proved that it should be at least as good. So it should be the same slope or better, I think. Any questions about that?
Cleaner question. When you sample X from M, how do you do that if M is just like a list of claims? Are there claims such that you can do that sampling?
Well, C is the claims. M is.
But for general functions, you can't do that. You can't draw a sample like that.
For general functions, meaning, I see, like you're applying this kernel thing. So yeah, okay. So I lied slightly here. I don't know if this is quite what you're asking, but I did lie slightly here. You should replace these expectations by an integral of the density function of M and F, which is like mathematically equivalent when M is like actually a density function, but also holds like the actual functions we use for M are not always positive. We're kind of like using these pseudo distributions, which are sometimes negative. So I kind of.
So F is something else too, basically. Like F is, yeah, that makes sense.
I think F might actually just be a function, but anyway, maybe I did sort of like sweep something onto the right here. Okay. So yeah, to summarize, so I think this problem, low probability estimation, I guess I argued that it's like captures at least some key part of the problem of safety guarantees, and And I think, yeah, I think it's an exciting direction. I think other people working on like white box approaches to safety should consider like asking the question, does my approach help with this problem? And yeah, that's everything I have. Thank you.
Connect the dots from some of the earlier things you worked on, like heuristic arguments and so on, to this.
Yes, good question. So I talked a lot about like white box and black box. And I kind of left those terms undefined. We saw maybe there's some gray box going on. It's not quite clear what's what. I think we have a more like philosophical perspective on what counts as like a white box approach versus a black box approach, which is more based on the idea of does this give us some reason to understand why the network works? So we kind of think of random sampling as being like simply verifying that a property holds and not actually telling us why it holds. Whereas we think that like an algorithm that looked a bit more like this would be telling us, in some sense, be telling us why the property holds, because we'd be kind of like doing some deduction at each step, going from one distribution to the next and saying, the reason this holds, yeah, it's like a deductive argument. So we kind of have this like sort of somewhat philosophical distinction between a deductive argument and an inductive argument. And this paper we have on heuristic arguments is all about this idea of like, can we actually formalize this notion of what it means to be like a deductive argument in this sense?
So I can think of this as like one route to producing a kind of bounding complexity approximation to the model. It's like fitting into this.
Yeah, maybe something like that. Yeah.
So in the empirical part from earlier, you're talking about predicting a rare token.
Yeah.
Like if I think of the vision of what the empirical setup would be for what you ultimately want, what is that?
I don't know how compelling my answer before was about sort of imagining you have a model followed by like some other model that's doing some like running a bunch of checks. If that's compelling at all. Should I say that one again or?
But like that other model, I guess, like trained it to do detection for catastrophes of some sort.
Yeah, I mean, I think like I say, we tend to approach. We're trying to approach this. We're trying to bring theoretical tools to this, and so we have done some simplification by like saying that we're replacing our informal notion of a catastrophe by a formal one. Okay, some reasons why we sort of think that's okay, at least for now, is like so yeah. Firstly, yeah, if you could maybe train another model to like detect problematic things, then that does kind of then give you a formal definition of catastrophe. But I think in practice we have thought a little bit about how do you actually combine like heuristic arguments with like some more traditional empirical approaches. Like I guess maybe a related question, which is not quite what you asked, but this input distribution, again, we've like changed it from something that's like fuzzy and undefined to something that's formally defined. And there may just be like things that the model learns, which are just like empirical properties in the input distribution, which have no reason, like there's no explanation for it. And so we thought a little bit about like, how could you combine an algorithm like this with some kind of like approach that lets you sort of empirically spot regularities? But yeah, we don't really have a very crisp answer there right now. So maybe that's not super satisfying.
Can I just say one note in the classifier setting? If you have the model and then a classifier, you can, with this approach, make the classifier take exponential time. Like you can give it an input, which is some enormous sample of random bits. And so I think there are, you could, if you solve this, you could do something that's quite a lot stronger than just sort of filtering outputs.
To ask if you've thought about what the algorithm for the claim chain might be. I was thinking about sort of linear relaxation through image practices.
Yeah, I'm not familiar with that particular algorithm. The sorts of things we've been thinking about. I think maybe one similar approach is like belief propagation. And we've kind of looked at sort of variants that look somewhat like that, but I don't have a good way of describing them succinctly.
Any other questions?
Thank you.
Thanks.
Right, yeah. Good things have to end.